Good morning. My name is David Kresse, Director of Systems Engineering at Nextracker. Today we are talking about PV module failures observed during recent high wind events. I want to credit Mr. Tushar Guha, Doctor of Aerodynamics at Nextracker, and Scott Dana at NREL for their support in this project. I'll be sharing some background on our test facility at NREL. We will look at conditions during and after recent high winds. We will also have measurements of differential air pressure and accelerations which the modules were exposed to, and we make a rough estimate of the peak stress on the PV glass. This presentation is a short introduction to some of our field test observations. Our goal is to raise awareness of the loading on PV modules installed in this location, and to work with PV module experts going forward toward a better integration of PV and mounting structures and the development of better PV qualification tests. Nextracker has two arrays installed at the Flatirons campus. One of the arrays is a 1-in-portrait or 1P configuration, and the other is a 2-in-portrait or 2P configuration. Each array includes 9 rows, which assures proper development of the airflow patterns corresponding to exterior and interior row configurations. Data acquisition includes over 600 channels of wind, air pressure, force, strain, torque, acceleration, displacement, video, and status data. In this image, we're looking roughly west towards the Rocky Mountains. The gap in the range to the right is called Boulder Canyon. Winds at the site originate in the mountains and accelerate through Boulder Canyon and out across Flatirons campus. This image was taken during one of the December high wind events, and dust from the cement plant just upwind of the test site is also evidence of the high winds on that day. There were 2 excellent wind events on December of 21. These curves are reporting peak wind speeds at a 10-meter height from the NREL M2 meteorological tower. Both events had winds exceeding 50 miles per hour for roughly 8 hours and peaks above 90. We consider these ideal wind events for data collection. Both included winds approaching the design wind speeds, and both occurred during daylight hours. On this slide, we have a 20-second video recorded during the high winds. But before I play the video, I'd like to identify a few features we can see in this view. We are positioned under the 1P tracker looking south towards the 2P tracker. The 1P tracker is tilted at 30 degrees into the wind, and the 2P tracker is flat. Wind is blowing from the right to the left. In the center of the view, we can see the last foundation pile of the 1P tracker with 2 dampers mounted to it, which is also partially obstructing the view of the 2P tracker beyond it. At the top of the view, we can see the 1P torque tube with accelerometers mounted to it. We also have a time series and a graphical overlay of wind speed and direction to the left. And I should also mention this camera is using a lower frame rate, so there's a great deal of camera shake. Observations you might look for include the torsional stability of the trackers, flexibility of the 1P torque tube, and of rapid changes in wind speed. So let's play the video. And let's play that again. After the high winds, the trackers were not damaged at all, so they continued to track as usual. However, we saw failed modules on both 1P and 2P trackers, and for this presentation, we're focused on the failed modules on the 1P tracker system. In the photo, we can see a grouping of 4 modules at the midspan of the second bay with broken glass. These PV modules are dual glass bifacial type, and each layer of glass is heat strengthened 2 millimeters thick. I also want to point out the white panel at the end of the row to the right. This is one of 18 differential air pressure measurement panels I'll be talking about in the next slide. Nextracker partnered with CPP to design and manufacture a system to measure differential air pressure in the field. The resulting panels have the same aerodynamic profile as a standard PV module, and each panel has 10 channels in different quadrants to measure the variation of pressure across the PV surface. Using these panels, we're measuring pressures at different locations within the tracker arrays, including exterior, interior, edge, mid-bay, and last row positions. This is an industry first to measure air pressure directly on the surface of the PV at full scale. And without going into details, I will say this has not been easy to do. The key benefit of full-scale measurement is that we can capture the full atmospheric turbulence spectrum and resulting frequency response of the wind. In particular, the higher frequency ranges, roughly above 5 Hz, cannot be reproduced in the wind tunnel due to limitations on the size of gusts. In this regard, measurements we're making at full scale are more comprehensive than wind tunnel testing, and even David Banks has referred to our measurements as ground truth. Here's an example of data from one pressure panel during the wind event of December 15th. During this 5-minute window, winds are peaking at 70 miles an hour. In the time series, we see momentary peak pressures reaching 700 pascals, and I should note these are point pressures at each sensor location that do not include area averaging. Looking at these measurements, we get a feeling for the dynamic character of the wind, but the magnitudes are not high enough to explain failure of the PV glass. Moving on, we conducted an evaluation of torque tube accelerations for the torsional, heaving, and snaking directions at the same mid-bay position as the failed modules. And to clarify, torsion refers to rotation about the center line of the torque tube, heaving is the direction perpendicular to the PV glass, and snaking is in plane with the PV glass, regardless of the tracker tilt angle. Here we are showing data for the heaving accelerations, since they have an order of magnitude greater influence on module stresses than motion in the other directions. The plot shown includes accelerations from 4 sensor pairs during the same 5-minute time series as the pressure measurements on the previous slide. We can see the peak accelerations are near plus or minus 10 meters per second squared, or plus or minus 1 g. At least for the tracker structure, accelerations of this magnitude are no concern at all. But we don't know about the PV. This slide is an analysis of energy density in the frequency domain of the heaving accelerations shown on the previous slide. This plot includes 4 traces from exterior, interior, and last row trackers. We can see that the spectrum includes significant energy in the range from 3 to 8 Hz. And putting this into context, for many years, structural analysis of trackers has focused on the first torsional mode, which most often has a single peak in the range of 1 Hz, and this behavior is well understood. Similarly, a heaving mode near 3 Hz could be expected for any tracker or fixed tilt structure, yet the peaks at 4, 5, 6, and the energy above may not be predicted and could be indicative of higher level interactions that are not accounted for in wind tunnel testing or the usual structural analysis. Again, for the tracker structure, this is not particularly concerning, but we're not sure if the PV modules may or may not be sensitive to these frequencies. As a next step, we calibrated a finite element model of the tracker and modules with the accelerations measured in the field. From the FEA model, we extracted the predicted accelerations at the edge of the PV frame and glass. In this plot, we can see those accelerations turn out to be 20 meters per second squared, or 2g, roughly double the measured response of the torque tube. Also using the calibrated FEA, we made an estimation of peak stress in the PV glass. In this graph of von Mises stresses, we see peaks exceeding 100 megapascals, which is high compared to the mean modulus of rupture for heat-strengthened glass. Plus or minus 1G at the torque tube does not sound like it would have much influence, yet these findings suggest the combined effects of wind pressure and modest accelerations could be a cause for higher stress on the PV glass than expected. From a structural perspective, plus or minus 1G is not significant, and we can already estimate situations where higher accelerations could be measured. Considering the industry overall, values of this magnitude or more are likely to be found on most trackers and fixed tilt racking systems when exposed to high winds. Granted, aspects of this presentation are a simplification, and there are several contributing factors we have not addressed. But our goal is to open a dialogue on the interactions of support structures with PV modules to improve our industry and our products. In summary, during the wind events of December, the peak wind pressures that we measured were modest and not the cause of glass failure. FEA analysis indicate that heaving is the load direction to be concerned with for stress on the PV glass. And heaving accelerations of plus or minus 1G at the torque tube or main beams of a support structure should be expected, and even higher values are likely. As a result, we might anticipate more PV glass failures due to the combined effects of air pressure and vibration during high wind events. For recommendations, Nextracker R&D is actively working to characterize tracker performance under a wide range of conditions and operational scenarios. And related to this particular subject, we plan to include accelerometers on the PV glass for comparison with the torque tube acceleration measurements we've already taken and to confirm the FEA assumptions. Beyond this, we suggest a program of vibration testing of PV modules to characterize their sensitivity to different accelerations. And long term, there's a need for standards to better define the interface between the PV modules and the support structures. Nextracker is interested in supporting further evaluations in these topics, and I'll be available at the Q&A session later. Thank you.